Welcome to our deep dive into the fascinating world of pathological science. In this video, we'll explore what happens when scientific research goes astray, not because of fraud or deliberate deception, but due to subtle biases, wishful thinking, or misunderstood data. Pathological science is a term coined to describe cases where scientists, often unintentionally, convince themselves and others of results that aren't actually real. It's a phenomenon that can affect even the most well-intentioned researchers, and understanding it is crucial for anyone interested in the scientific process. Let's begin by defining what pathological science really means and why it matters. Phrase pathological science was first introduced by Nobel laureate Irving Langmuir in the 1950s. Langmuir observed that sometimes scientists could become so invested in their experiments that they would see patterns or results that weren't truly there. He compared this to a kind of scientific illness, where the normal checks and balances of the scientific method break down. This concept has since become a cautionary tale in the scientific community, reminding us all to remain vigilant against self-deception and to maintain rigorous standards. Pathological science is marked by several distinctive features. Often the effects observed are barely detectable and require highly sensitive instruments. The results tend to disappear when experiments are repeated under stricter controls. There's usually a strong emotional investment from the researchers, and the findings are often defended vigorously despite mounting skepticism. These characteristics make pathological science particularly tricky to identify, as the line between genuine discovery and self-delusion can be very thin. One of the driving forces behind pathological science is wishful thinking. Scientists, like all humans, can become attached to their hypotheses and may unconsciously interpret ambiguous data in ways that support their beliefs. This isn't about dishonesty, it's about the subtle ways our minds can trick us. When researchers want something to be true, they might overlook flaws in their methods or ignore contradictory evidence, leading to conclusions that don't hold up under scrutiny. One of the most famous cases of pathological science is the story of N-rays. In the early 1900s, French physicist Prosper Blondlot claimed to have discovered a new form of radiation. Many scientists eager for groundbreaking discoveries reported seeing N-rays too. However, when more rigorous tests were conducted, it became clear that N-rays didn't exist. The initial results were likely the product of suggestion and expectation, not actual physical phenomena. Another classic example is polywater, a supposed new form of water discovered in the 1960s. Researchers believed they had found a variant of water with unusual properties. Excitement grew and many labs tried to replicate the findings. Eventually, it was revealed that the strange properties were due to contamination, not a new substance. The polywater episode highlights how easily excitement and groupthink can lead scientists astray. 1989, two chemists announced they had achieved cold fusion, a process that could potentially provide unlimited clean energy. The scientific world was electrified and many rushed to replicate the results. However, most attempts failed and it became clear that the original findings were not reliable. The cold fusion saga is a modern reminder of how even experienced scientists can fall into the trap of pathological science when the stakes are high and the desire for success is strong. Pathological science often arises from subtle biases that creep into the research process. Confirmation bias, for example, leads scientists to focus on data that supports their expectations while ignoring contradictory evidence. These biases are rarely intentional, but they can have a powerful effect on how experiments are designed, conducted, and interpreted. Recognizing and mitigating these biases is essential for maintaining scientific integrity. Application is a cornerstone of the scientific method. When a result is genuine, it should be reproducible by other researchers using the same methods. Pathological science often fails this test. Results that seem promising at first can't be replicated under controlled conditions. This is why the scientific community places such a strong emphasis on independent verification and peer review. Scientists are passionate about their work, and this passion can sometimes cloud judgment. When researchers become emotionally invested in a particular outcome, they may unconsciously interpret ambiguous results in ways that support their hopes. This emotional investment can make it difficult to accept negative results or criticism, further entrenching mistaken beliefs. Peer pressure can also play a significant role in pathological science. When a scientific community becomes excited about a new discovery, there can be subtle pressure to conform and report positive results. This can lead to a bandwagon effect where skepticism is discouraged and critical voices are drowned out. Such an environment makes it even harder to spot errors or biases. Media can amplify the effects of pathological science by sensationalizing preliminary findings. When exciting results are reported before they've been thoroughly vetted, public expectations can soar. This puts additional pressure on scientists to confirm the initial claims, sometimes at the expense of careful, objective analysis. The cycle of hype and disappointment can damage public trust in science. Overinterpreting ambiguous data is a common pitfall in pathological science. When results are unclear, it's tempting to read too much into them, especially if they seem to support a favored hypothesis. This can lead to a cascade of further errors as subsequent experiments are built on shaky foundations. Careful, critical analysis is essential to avoid this trap. Today, the scientific community has developed numerous safeguards to prevent pathological science. Peer review, replication studies, and open data policies all help ensure that findings are robust and reliable. While no system is perfect, these measures make it much harder for mistaken results to go unchallenged. Scientists are also encouraged to pre-register their studies, which helps reduce bias and increase transparency. Healthy skepticism is a vital part of the scientific process. Questioning results, demanding evidence, and being willing to change one's mind in the face of new data are all hallmarks of good science. Pathological science thrives in environments where skepticism is discouraged. By fostering a culture of critical inquiry, we can help guard against self-deception and error. Every episode of Pathological Science offers valuable lessons. By studying past mistakes, scientists can become more aware of the pitfalls that lead to error. This historical perspective helps researchers develop better experimental designs, more rigorous controls, and a greater appreciation for the complexity of scientific discovery. Mistakes, when acknowledged and understood, can be powerful tools for progress. At its core, pathological science is a reminder that science is a human endeavor. Researchers bring their hopes, fears, and biases into the lab just like anyone else. Recognizing the human element in science doesn't diminish its value, it makes it more relatable and ultimately more trustworthy. By acknowledging our limitations, we can strive for greater objectivity and honesty. Pathological science isn't just a relic of the past. Even today, new cases emerge where researchers become convinced of results that later turn out to be artifacts or errors. Whether it's in medicine, physics, or psychology, the risk remains. Modern technology can help detect errors more quickly, but it can also introduce new forms of bias and overconfidence. Advances in technology have transformed the way science is conducted. Sophisticated instruments can detect signals that were previously invisible, but they also make it easier to misinterpret noise as meaningful data. As technology becomes more complex, the need for careful calibration, validation, and skepticism grows ever more important. The open science movement is helping to combat pathological science by promoting transparency and collaboration. By sharing data, methods, and results openly, researchers make it easier for others to verify findings and spot errors. This culture of openness is gradually making science more robust and less susceptible to the pitfalls of self-deception. In the 1960s, scientists claimed they could transfer memories between flatworms by feeding trained worms to untrained ones. The idea captured the public's imagination, but later studies failed to replicate the results. This case illustrates how extraordinary claims require extraordinary evidence and how easy it is for wishful thinking to influence interpretation. Peer review is one of the main defenses against pathological science. By subjecting research to the scrutiny of independent experts, the scientific community can catch errors, biases, and overinterpretations before they become accepted as fact. While not perfect, peer review is an essential part of maintaining scientific standards. Negative results are just as important as positive ones in science. They help prevent the spread of false ideas and keep the scientific record accurate. Unfortunately, there's often less incentive to publish negative findings, which can allow pathological science to persist longer than it should. Encouraging the publication of all results, positive or negative, is key to scientific progress. Groupthink can be a powerful force in scientific communities. When everyone is eager to believe in a new discovery, dissenting voices may be silenced or ignored. This can allow errors to go unchallenged and lead to widespread acceptance of flawed ideas. Encouraging diversity of thought and open debate is essential for healthy science. Funding pressures can sometimes contribute to pathological science. When grants and careers depend on producing exciting results, researchers may feel compelled to interpret data optimistically or rush to publish. This environment can make it harder to admit mistakes or pursue negative results, increasing the risk of error. To safeguard against pathological science, researchers must cultivate humility, transparency, and a willingness to be proven wrong. Building strong collaborations, seeking out criticism, and prioritizing rigorous methodology all help reduce the risk of error. Ultimately, the best defense is a culture that values truth over ego. Despite its flaws, science is fundamentally self-correcting. Over time, errors are discovered and mistaken ideas are replaced by better ones. This process can be slow and sometimes painful, but it's what makes science such a powerful tool for understanding the world. Pathological science is a reminder that the journey to truth is rarely straightforward. Critical thinking is essential for both scientists and the public. By questioning assumptions, evaluating evidence, and considering alternative explanations, we can all become better consumers and producers of knowledge. Teaching critical thinking skills at every level of education helps build a more resilient scientific community. Looking ahead, the future of scientific integrity depends on our ability to learn from past mistakes and adapt to new challenges. As science becomes more collaborative and global, maintaining high standards of honesty, transparency, and rigor will be more important than ever. By working together, we can ensure that science continues to serve the public good. Conclusion: pathological science is a cautionary tale about the limits of human perception and the importance of rigorous methodology. By staying vigilant, embracing skepticism, and fostering a culture of openness, the scientific community can minimize the risks of self-deception. Science is a journey, and while mistakes are inevitable, each one brings us closer to the truth. Thank you for joining us on this exploration of pathological science.